This is AP Calculus, Lesson 8, in our chapter on properties of limits, or our unit on limits. So this lesson is about properties of limits. You're going to learn some properties. You need to make sure that you are memorizing these properties because we're going to be using them a lot. All right, so here we go. So first of all, we said that the limit as x approaches c of some function can be evaluated just simply by substitution, meaning just plug in the c into the function, only if the following conditions are happening. If the function is continuous, meaning there's no breaks and bumps and all that, and defined at that c. And I should say what I mean by continuous is it's continuous at the c. So it might be not continuous elsewhere, but at where x equals c, there can't be any jumps or holes or anything else. It needs to be continuous at this c and defined at that c. So here's your first example, and it's a graphic example. So if we look at this function right here, we say, oh, it's a linear function, and this one happens to be continuous everywhere, but most specifically it is continuous right around the point where x equals 2. And not only that, at x equals 2, it has a value on the graph, which is 1. And so that is the limit as x approaches 2. You simply just plug it into the function, or in this case, look at the graph and you can see it. Let's look at a second example. And in this example, we have a function that we know is continuous. Now, it's not continuous everywhere. It has a place where it begins because we're looking at this as a square root of this cubic function. And if we were to look at that on a graphing calculator, we'd see that it might have some kind of a place where there's nothing in the domain. But, because you can't have a negative under here. But around the input of 2, it is continuous. And so then we just plug in the 2 into this function and evaluate, and we find that the answer is 5. So let's talk about some basic limit laws. And these are ones we need to know, we need to memorize, we will be using them. So first of all, we have to define two limits because we're going to talk about how these two different limits work together. So we have the function f, and I'm saying that as x approaches some c, some constant number, this function does have a limit, and the limit we're just going to say is L, which just represents some real number. Okay. There's a second function, g, that when we have the limit going to the same c, this must be the same c. And this other function, g, has a limit, and its limit is some other real number. It could actually even be the same. It doesn't make any difference. It just has a limit. So we're going to use those two functions and their limits, the function f and the function g, and their limits as x is approaching some constant number. And the first thing is we can look at this as the limit of the sum. So it's a limit of the sum of those two functions. Well, the limit of the sum is the sum of the limits, meaning we can break up over addition. And then since we know that the limit as x approaches c of f of x is L, and the limit of as x approaches c of g is k, then we just do L plus k. Now this is for addition. It's the same thing as if it were subtraction. So if we had a limit of a subtraction, then it's the subtraction of the limits, and we'd have L minus k. So that's actually kind of like rule 1a and rule 1b. Rule 2 is when you have a product. So we have a limit of a product, and a limit of a product is the product of the limits. So we end up just multiplying L times k. Rule 3 has to do with division. The limit of a quotient is the quotient of the limits. So if I say the limit of these functions being divided, well, we can just do the limit of f and then divide it by the limit of g, and we have L divided by k. This one here is I have a limit of a function raised to a power. So if I had the entire function raised to some exponent, we can instead just evaluate the limit of the function and then take that value and raise it to the exponent. So we end up with L to the n. Okay, because this is saying it's no different than saying the limit of x squared is the same thing as the limit of x and then squared. Okay. And 5 is about multiplying by a constant. So if I have a limit of a function times a constant, we can take that constant out of the limit speak here and put it in front and say, oh, it's the constant times the limit. So you end up a times L. Okay? Let's use these in a couple of examples. So first of all, we have to define two limits. We have the limit as x approaches 2 of f of x, and we have the limit as x approaches 2 of g of x. Now make sure they both have to have the limit as x is approaching the same value. For f, that limit is -3. For g, that limit is 5. So our first example is, well, what if we had the limit of f minus g? Well, that would just be -3 minus 5, because it's positive 5. And we end up with -8. If we have the limit as x approaching that 2, it has to be the same number everywhere we go, the limit is x approaching 2. The product of the functions, so if I knew the functions, I could multiply the functions, but we don't need to, because since this is limit, I can just multiply their actual limits, so -3 times 5, which is -15. And in our last one, we got a couple things going on. We have a quotient, we have a division going on, and we have multiplying by a constant. So the first thing I'm going to think of is I'm going to pull that constant out in front, and then I'm just going to do the limit as x approaches 2 of f of x divided by the limit as x approaches 2 of g of x, which would end up looking like this. And our answer is +3. So those are your rules of limits with a few examples. We have one more problem that you're going to do. You're going to do the best you can at drawing a sketch of this thing. And then you're going to bring it to class, and we're going to examine the different things that people did, because in this next problem, you're not all going to have the same answer. And that problem is this. This is your do now. As you're doing this lesson, I want you to do this now. And that is, you're going to sketch a graph, okay? And it has to fulfill all of these conditions. This isn't just, one graph, a second graph. No, this is one graph, and it needs to fulfill all of these conditions. The limit as x approaches -2 from the left of the function goes to 5. So remember what that means. Doesn't just, okay? And then you have the limit as x approaches -2 from the right is going to equal 0. The limit as x approaches 3 exists. They're not telling you what it is, but that it exists. The limit as x approaches 5 doesn't exist. The function at 3, oh, that's different. The function at 3 versus up here where we had the limit as x approaches 3. This says the function at 3 is undefined. Now that means something specific in the graph. And then lastly, the function evaluated at 5 equals 2. Now remember, up here, it said the limit as x approaches 5 doesn't exist. The limit doesn't exist. But it does say the function at 5 is 2. So draw a function that fulfills all of those conditions. Make a sketch of a graph. So you have to have, your numbers on your number lines and things as you do this. And then we're going to compare what different people got in class, right? There you go. When you finish this and have your notes, work on your homework.